Well, thank you very much, Daniel, for the invitation to talk and for having us. And also to the rest of the MFEM team. What I'm going to be presenting is the work we've been doing under an SBIR phase 1 project entitled The Development of a Cloud-Based Web Application for Wellbore Stability Analysis. So we are wrapping up that project this week, so we are supposed to finish with everything. So our company, OpenSim Technology, we are based in Houston, and we founded the company in 2016 with the objective of developing software for the oil and gas industry, basically. So we spent the first 4 years developing a reservoir simulator coupled with geomechanics, which is right now in the back burner. Our team combines a lot of experience in developing this kind of software for the oil industry from different points of view, which includes national oil companies, research institutions, and oil company, private oil companies as well. So I am the PI for the project. I have a PhD in physics, and I've been working. I have more than 20 years of experience developing this kind of software. Jorge is a PhD in chemical engineering, and Natalie is a computer science, has a computer science degree, and she's been doing many different things for this and other projects. The idea, let me introduce the idea of wellbore stability in just one slide, because it's a relatively simple problem with a lot of implications at the same time, right? So a wellbore in the, it's, if you drill a wellbore in the subsurface, this can be done for many different purposes. The most common one is for production of oil or hydrocarbon production, or it can be for injection, or it can be also applied to geothermal energy production or CO2 sequestration. And these wells can extend for thousands of feet, and they can have a very tortuous path underground. So what happens if you drill a well underground and you don't do anything, is most likely it's going to collapse. So to avoid this, a mud is typically used to prevent the collapse of the well, but the mud has to have the right weight, otherwise, if it is too low, the well is still going to collapse. And if it is too high, you're going to break the formation, and you're going to lose the mud. So the idea is that within this kind of complex geometry, relatively complex geometry, certainly is not as complex as some other problems that we have seen here, how to prevent the failure of this well in any direction and optimize the mud weight. So that's the objective of this kind of applications. And in terms of the physics, it can be more complex than this, but this is what we are doing right now. We are solving the mechanical equilibrium equations for linear elasticity. And of course, we're using MFEM to do this, and we're using PyMFEM in this case. And the boundary conditions can be sort of an issue. So because basically you want to represent the in situ stresses and also the pressure inside the wellbore as dictated by the mud weight that you're applying. So these boundary conditions are a function of depth, basically. So typically, the most simple case will be dictated by a gradient, right? So basically, you have a function, and it is a very simple function. Some other times, it may be a more complex function, especially for the in situ stresses that can change with the type of formation or something. But in this case, we're just using a gradient with depth. So the other part of the problem, so the first part of the problem is how to create this geometry. So we designed an application in a way that we can create synthetic wells, and also we can, in principle, represent an existing well if we know the right information. Right? So what we are doing here is we are representing the well in a series of segments of a given length, and then we specify the inclination and azimuth at the beginning and end of each one of the segments, and the trajectory is going to be interpolated in between. So the problem is that if you try to represent this wellbore with a single grid, it's going to be a very big model, typically. So what we are doing right now is that we say, okay, we will split the wellbore into multiple segments. Basically, we're saying how long, how big the segment is going to be. So in this case, we are specifying, we have a 400 meter well, which is relatively small, and we are specifying 30-meter maximum length for each one of the boxes. So we can play with that right now. In this case, we have about 11 different pieces, and then basically we are going to solve the problem on each one of these pieces. Next step is to use discretization. We are using GMesh at this point, and the idea is to have a grid so that is very refined around the wellbore in order to capture the stresses accurately around the wellbore, and then extend and make it coarser as we move away from the wellbore. So we have some parameterization. It's working for now. It may not be the best, but we are still working on that. So I'll show you some of those grids in a future slide. So these are some of the segments that you see. The first 5 of those segments. You see that the boxes will have to be of different shapes in order to capture the geometry, and also you don't want the wellbore to be too close to the external wall. So that's one of the parameters that we specify. How far we want or how close the wellbore will be to the wall. And this is an example of the first piece of the well. You see there is some curvature there, and from the top view you can see the refinement around the wellbore. So this is a relatively simple example with many different pieces. So we never have a box that is too big, or a piece of wellbore that has a big angle or something. So then we solve this linear elasticity problem. This is the kind of things that you're going to see for the displacements, and it's not terribly interesting, except for the proximities of the well, right? So here you just see the deformation of the full box, and I think this corresponds to the fourth one here. So now the next step is to compute, well, this is to show how the stresses are distributed. I mean, the displacements in the x direction are distributed, and in the proximity of the wellbore as well. So we implemented a stress coefficient class in MFEM in order to compute the stresses after the displacements have been computed. And these are the results for that. And you can see that that there is a lot of fluctuation in the stress around the wellbore. However, they follow the expected pattern, right? So, but still, I think part of the fact is the grid is not refined enough, but also it's not necessarily adapted to the shape of the well. So that's going to be important, but because that's exactly where we are going to do the analysis. So we're going to show you how we are dealing with that issue. And before we get to that, let me show the scalability. This was a really interesting experience here because we started at the beginning, we were solving the problem in just one core. So we were doing serial runs, and we realized that the stress calculation was taking way too long. So you can see here the solution for the displacements was taking 384 seconds for this particular problem, which is has about 1.5 million degrees of freedom. And the stress calculation was taking 500 seconds. But when we started working in parallel, we realized that the stress calculation was really improved with a number of processors. And this is to be expected, right? Because the stress calculation is a calculation that is embarrassed in parallel. So we expect that. So this was a good news. Still, it takes some time, right, to do this, half of the time as it takes to get a solution. So that's something that can be a point of that we need to pay attention, especially because we will need to run grids that are much bigger than this one. So the solution that we found for now, and I think this is working really well, is to project the solution, is to create a second grid concentric with the wellbore at a particular location where we want the stresses to be computed and the analysis, because this is a typical situation with wellbore stability analysis. You have a problematic region. You don't want to compute the stresses everywhere, but only in that particular region. So we created this secondary grid and then place it concentric with the wellbore at a particular location, and then projected the solution there using the fine grids functionality in MFEM, fine points. And then we just need to project the displacement, so we don't need to compute the stresses in the full grid. We project the displacements, and then the stresses are computed only in this partial grid, and this smaller grid. That's still some noise, but of course there will be some noise because you still have the problems originated by the solution. But we can do an additional trick, and is to smooth out the solution in the axial direction to the grid. So we will be losing some of the physical behavior, but it's a relatively small section of the well, and that actually improves the solution a lot. Probably something that we will remove later when we have a better solution, but for now, this is producing better results. The next step is to apply some failure criteria. In this case, we are using the simplest possible one, which is Coulomb, which is described by these figures over here. So it's very simple. So basically, what we did was to compute the principal stresses around the wellbore on that ring, and then convert this equation into an index so that if it is positive, the wellbore is going to, the region is going to fail. Basically, this is what it's telling us. Since we are solving linear elasticity, many of those points can be in the failure region, and nothing is going to happen, guys. There's no plasticity or any other calculations that we are applying there. So, but this is a typically done in wellbore stability analysis, because you just want to avoid that situation. You don't necessarily want to compute the post-failure behavior. So, so this is an example for a section of the well and multiple rings where we projected the solution, computed the stress, and computed this index to see where the problematic areas will be. And in this case, for this particular parameters, this is going to fail everywhere, basically, because most of these numbers are positive. except for the blue region. So you definitely don't want this to happen, right? So this is an example. We run it for 2 more values of the mode weight, the higher values of the mode weight. And if you remember this plot, when the mode weight is too long, you're going to have a situation like this, which is called a washout, which means that you are going to, all that region around the wellbore is going to break down and, fall by gravity or be dragged by the mud. If you increase the mud weight, then you're going to have shear failure. So this starts to be acceptable because everybody knows that you need to accept some failure in the well. It's not going to be perfect. But if you continue to increase the mud weight, you are now going to create a fracture, right? So I start losing your mud. So these are the 3 results for this situation, for the extreme situations. In this case, the one I represented before, this is well, actually this is Coulomb index. And then as we increase the mud weight, you can see that, and here the purple region is the region where the Coulomb index is positive, which means that it's going to fail there. So this is going to be a washout, right? So similar to that one. Then you reduce that area, and this may be acceptable depending on the situations. But if you continue to increase, now the failure region switches to the other 90 degrees basically, and now you are creating fractures. So that's what is going to happen probably. And finally, what we are doing is implementing a Webapp and develop this into the cloud and Amazon Web Services. So we are in the middle of this. We already created our Docker images, and locally they are working. And we have deployed a prototype in Amazon Web Services, which we can run, on any device. And the only thing that we are missing at this point is the visual part, which we still don't know how to handle, but we hope to get there very soon. And this is my presentation. I think I still have some 3 minutes for questions if there are any.
So for this web app, are you hoping that engineers sort of out in the field, it'd be easy enough for them to use at that point?
Yeah, that's what we hope. Yes. So these conversations with the engineers typically is on the field where you really want to have this application, because there's no enough time to typically to communicate and start for the studies to happen, right? So if you can do that in the field, it's the ideal situation. That's why we are trying to do this, so you can use it from a device, a handheld device.
How much time do they have to make a decision before they fracture or munch the whole operation out?
Well, I think these things happen within, depending on the kind of well, right? On conventional wells, for example, it can happen very quickly. We're talking 1 week, so it's not going to happen in 1 hour for sure.
Okay, so they got a little bit of time to do some analysis and figure out what's going on before it all falls apart.
Exactly. Yeah. So the code runs in a few minutes, so it should be okay, right? So I think so. Typically, you need to run many different situations and find the optimal. But still, I think 1 hour should be okay.